So Philipp Hoehn will talk about a perspective-neutral approach to quantum general covariance. Excuse me, from the University College London and OIST.
Right. Yeah. So this is some work. Oops. Sorry, that was not what I wanted to do. Yeah, this is a lot about structural relations here. So it's about studying the fate of general covariance in the quantum regime. When you take serious that reference frames are always quantum systems themselves. And so this touches a bit on some of the discussions that we have had previously here, namely on how different perspectives or quantum reference frame perspectives can consistently be fit together. So this is work that has been done in collaboration with various other authors. One of them is actually sitting here in the audience, I guess, Augustin van Rietvelder, somewhere in the back. So he's that guy. Right. So yeah, let's get started. Does it work? Oh, it's right. Counterintuitive. Yeah, so this has something to do with general covariance. So just as a brief recap or motivation, so general covariance, at least colloquially speaking, is usually interpreted as in the following sense, namely that all the laws of physics are the same in all reference frames. So that tells us already that there are some structures that are independent of the reference frame. Technically, we usually interpret that in the sense that physical laws are tensor equations, and indeed tensors are actually some really nice objects because they're in some sense actually reference frame neutral, right? So they basically encode the information about what all kinds of reference frames or any reference frame that you have in your space-time in GR would measure. So suppose you pick the energy momentum tensor, then you also have to tell me, for example, some vector frame. Then you can contract that energy momentum tensor with that frame, and then that will tell you what energy and momentum is measured in that kind of frame. And so these are very nice objects that are encode the information about all reference frames at once. And so they're quite powerful features. Now, technically in classical GR, what kind of structures do we use in order to make sense of this notion of general covariance? Well, we usually do that by idealizing reference frames. We kind of ignore that they have some internal dynamics or back react on space-time. We just may model them by some vector frame, for example. They're sort of painted onto space-time in a way. They're kind of external. So you may think of Alice and Bob traveling through space-time in some rocket ships. This you can actually interpret as a frame-neutral physics because that's a physics that's encoded in tensor equations usually. So in order to say that Alice and Bob are traveling through space-time, in order to make sense of that statement, I don't actually need to pick a reference frame to make that statement. But if I want to say how fast they're moving relative to, or how fast they're moving, then one has to pick a reference frame. So this we can, of course, do by, for example, saying that we model Alice by some vector frame that defines some coordinate map into some coordinate description of some patch of space-time. Could, of course, do the same thing relative to Bob. And then we can consider that coordinate description as Bob's perspective on the local physics in space-time. And, of course, if we want to go from let's say Alice's perspective to Bob's perspective, then we have that nice compositional structure of coordinate changes on a manifold that you all know about. So we have to invert Alice's coordinate map or Alice's perspective map. And importantly, we always map back into the frame neutral physics. And then we have to concatenate it with a forward perspective map or the coordinate map into Bob's perspective. Now, why am I reiterating here some stuff that you all know from GR? Or well, whatever, differential geometry. And the reason I'm bringing this up is because I want to ask whether we can actually recover some of these structures also in the quantum regime, when we actually take serious that reference frames, in fact, are always dynamical systems, that they're, in fact, also subject to the laws of quantum theory. And so then we may very well ask the question of what happens to that notion of general covariance when the reference frames are actually quantum. In particular, do we then also get such a nice compositional structure of how different quantum reference frame perspectives are related? And the question in particular is, in the quantum regime, what could be the role or play the role of something that we might call this frame neutral structure in between? That's kind of like the linking structure of the different perspectives. So just a little prehistory. So there hasn't been actually that much work in this direction. So in the context of quantum clocks, I've done some work during my PhD. But I would say that in recent years, there's been a resurgence of interest in this direction. In particular, it was kind of triggered by that paper here, again, coming from Vienna. It's one of the PhD students, Flamina Giacomini from Czeslaw. And so what I'm going to be talking about is sort of a synthesis of ideas here that's kind of converged into what we may now call a perspective-neutral approach, and this is what I will be talking about here in this talk. Okay, so let me just tell you very briefly what the basic strategy here is. So when we talk about general covariance in the sense of coordinate transformations, those are of course passive diffeomorphisms. And here what we want to do is actually transition from the focus on passive diffeomorphisms rather to active diffeomorphisms. So we're getting away from pure coordinate description and rather focus on the dynamical degrees of freedom. And this is also much better for quantum gravity because depending on the approach, but if we say do a canonical quantum gravity, then we don't have any coordinates anymore in the quantum theory. So this is the basic idea. The other thing is, so of course this will have something to do with symmetries, and the key implication here of the symmetries is that among the dynamical degrees of freedom, there will be a lot of redundancy in the description of the dynamical degrees of freedom. And that redundancy will allow us to make different choices of whatever degrees of freedom we might want to choose as a reference degrees of freedom relative to which we describe the remaining physics. Okay, so here's the plan of the talk. I will try to illustrate that that approach, this perspective-neutral approach in the relational n-body problem. So here I will try to be a little more conceptual, just to give everybody a bit of a feeling or intuition that it makes sense what I'm talking about here. Later on, I will talk about the holy trinity of relational quantum dynamics. So that's some kind of implications of that new framework for relational dynamics. So using basically temporal reference frames, if you want, quantum clocks. And then, if I have time, I may talk about also how these methods lead to changing quantum clocks or relational quantum clocks, but I'm not sure I will actually make it here. That part would be a little more technical, and then I would conclude. Okay, so the relational n-body problem. Yeah, suppose we have now here our 3D Euclidean background space, and now we throw some n bodies inside, and they're all, so this is 3D, so they're all described by each by a 6-dimensional vector. So of course, overall, we have a 6n-dimensional phase space. And now, so what do I mean by relational? Let's require that that whole system is actually invariant under global translations, such as this here. And let's also require that it's, in fact, invariant under rotations, such as this. These will, of course, transform these phase space degrees of freedom. And so it turns out, so those who are familiar with constrained systems, for those that will be trivial, the statement. For the others, you just have to believe that. If you do a canonical analysis of such a system, what you will get in the canonical formulation is presence of constraints. And constraints here in this form that the total momentum is required to vanish. And in fact, also the total angular momentum is required to vanish. Okay, so and as you can already see, these total momenta and total rotations, total angular momenta, they're also the generators of these symmetries under which I require invariance here. Now, this already tells you that we will get a redundancy in the description. So that's, of course, related to the symmetries here. Well, there's redundancy here, of course, because these relations have to be satisfied. That means these phase space degrees of freedom, they satisfy algebraic relations. So they're not all independent. Now, the question is, what is the physical information here, the gauge invariant information? Well, it's, of course, if we have invariance under translations and global rotations, then, all the relative distances are, of course, invariant under those, and also the relative orientations, so like here. Now, there is, however, also a redundancy in the physical information, because, of course, we could, once you know these two relative distances, then you will also know what that relative distance is, and so on. You can do all kinds of counting arguments. So you not only have redundancy in the description of your kinematical degrees of freedom, but also in your gauge invariant degrees of freedom. And so what's the idea here now? The idea is that we say that we interpret this redundant description. This theory doesn't tell you, of course, which of the degrees of freedom you're supposed to pick as the redundant ones. That's your choice. And the idea is that we interpret this redundant description as a so-called perspective-neutral description. So what does that actually mean? It's like a global description of the physics prior to having actually chosen a reference system relative to which you describe the remaining physics. Okay? And now, if we want to go to a particular perspective of a reference system, so here we can just pick some of the, let's say, particle A, and now we want to describe all the remaining particles from the perspective of A. So we can do that. That amounts actually to a gauge fixing. So what I want to say here is actually we always interpret the choice of what the redundant degrees of freedom as being actually the reference degrees of freedom. And why is that? Because we don't want to describe basically the reference frame relative to itself to avoid the self-reference problem. Okay, so fixing now to a perspective here is like choosing a gauge. We could, for instance, say that we just pick that particle A to be our origin. Then we could also say, well, B shall define this, the Z direction relative to A, and maybe C and B together are defining the ZX plane. One can show that that's a gauge fixing condition for these symmetries. And well, once you do that, the only dynamical degrees of freedom that you're left with are in fact dynamical degrees of freedom of only the remaining particles. Okay? So in a way, you can interpret this now as being a description of the remaining particles as seen from particle A. So everything is classical here, I should say. No? Now, of course, you could do the same thing relative to choosing particle B. You would have to choose accordingly different kind of gauge. It should be relatively clear that these different descriptions relative to different particle perspectives are in fact related by a gauge transformation, because we can, in order to go from A's to B's prescription, it's clear that we can just do by translations and rotations, put B into the origin, and then also rotate whatever other reference particles we want to use from the perspective of B to define the Z and X direction into the according positions. Okay? So that's just conceptually a summary of why this works classically for those who are a bit more familiar with constrained systems. So the idea here is that, so we have constraints in the phase space. There's a constrained surface. That constrained surface we interpret as the perspective neutral description of the physics, so the description of physics prior to having chosen a reference system relative to which we describe the rest. There's gauge orbits on that constrained surface, and like picking a perspective relative to one of the particles is equivalent to choosing some gauge here. So that amounts to some gauge fixing hypersurface in your phase space, and then the intersection of that gauge fixing hypersurface with the constrained surface that defines your actually reduced phase space. So it gives you proper phase space description, which the constrained surface doesn't give you. And then basically those gauge fixed reduced phase spaces we interpret then as the description of physics relative to whatever particle we have chosen. Now it's clear that these different gauge fixed reduced phase spaces are related by gauge transformations. So that's basically the more formal way of saying what I said before, that we can always go from the description relative to one particle to that relative to another by flowing along the gauge orbits in the constrained surface. If you want to do this a bit more formally, you can do this here in terms of embedding maps, gauge fixing maps, and so on. The main important thing is that from whatever reduced perspective to another, we can always do that by going back via the perspective neutral constrained surface, doing a gauge transformation, and then going to the other description. Okay, so now what we want to do is basically a quantum version of it. I will just be very brief here because I want to talk about this a little more in the context of relational dynamics, but I'm just giving you a bit of intuition. So I've told you that this classical constraint surface is like the perspective neutral description. So now we do the same thing in the quantum theory. So in order to do, we do a Dirac quantization. What that means, we first quantize all degrees of freedom. Here we do that on the R to the 3n, so the basically configuration space for all particles. And then we have to impose the constraints. In this case, the states satisfying these constraints are so-called physical states. They have to form a new Hilbert space that's actually, in this case, not a subset of that kinematic Hilbert space, but let's not worry about that too much here. And this is like the quantum constraint surface, okay? So that's like the quantum states satisfying the constraints. And now, there's again a redundancy in the description also in the quantum theory. And why is that? I mean, it's of course because these, on the physical Hilbert space, again, let's pick the x direction here, then of course, all the PIX operators, if you want, they're actually algebraically dependent on the physical Hilbert space. And they actually turn out to be also gauge invariant, so it makes sense to say that. And by similar reasoning, one can actually also argue that the other gauge invariant observables, so-called Dirac observables, are also algebraically dependent. And in fact, also in the description of the physical states, you get redundancy. You can write the same physical states in many different ways by writing it relative to different choices of coordinates. Okay, so, and that's roughly also why in the quantum theory we interpret the physical Hilbert space or the quantum theory on it, including the observables, as being the perspective-neutral quantum theory, so the global quantum description prior to having chosen a quantum reference frame. Okay, so now how does that work? In the quantum theory, we can actually also do so-called quantum coordinate changes. So we have then the perspective-neutral physical Hilbert space from Dirac quantization. So that's, we haven't chosen yet a reference system. And then what I told you before, so we now can also construct the quantum analog of these classical phase-space reductions. These classical phase-space reductions, they proceed by gauge fixing. I should say there's no gauge fixing anymore in the quantum theory once you solve the constraints, so it works a bit differently. I'm not going to tell you that in detail. You just have to trust me that it works. This has been worked out with Augustin. That was part of his, I guess, first master's thesis by now. And so what is that actually doing? So it's so these are maps, quantum symmetry reduction maps. They're always relative to a choice of reference system, here relative to particle, that remove essentially the redundancy in the description. Okay, so if we pick, again, particle A, well, it basically removes all reference to particle A in the description, and it gives you the so-called reduced Hilbert space. You can do the same thing relative to B, and then these quantum symmetry reduction maps, they're sort of like the quantum coordinate maps, if you want. They are not always globally invertible, depending on the model. But wherever they're invertible, you can basically embed the information that's in one quantum reference frame perspective back into the perspective-neutral structure, and then map it forward using the quantum symmetry reduction relative to the new frame, and then go to the new quantum reference frame perspective, and that gives you also such a nice compositional structure as I was indicating before for general relativity, except that here we're working between different Hilbert spaces. Okay, so and one of the most important things here to note is you should always note that we're always describing the same physics, but from different quantum reference frame perspectives. And the same physics is the one that's encoded here in the physical Hilbert space. It may appear differently from the different perspectives, but it's always the same physics. Okay. Yeah. So here's actually, there's an operational consequence of these constructions. So this is actually taken from that paper that I was referring to before, involving also Časlav. So they were constructing such, so this here is for one dimension. And if you restrict our model to one dimensions, then we recover quantum reference frame transformations that were previously constructed in a different approach, not involving symmetries or this perspective-neutral language or constrained systems. But yeah, what they showed in that work is quite cute. So you find actually that, so what you always have here is different quantum states seen from different quantum reference frames. So for instance, this one is quite cute. So this is a state of particles A and B. So it's like a 3-particle scenario as seen from C. This here is so they're entangled A and B. That's what's indicated here, but with a fixed relative distance. And if you now apply such a quantum reference frame transformation that I haven't actually given you explicitly, but that you can construct from what I showed you in this general scheme before, then you can translate that, for instance, to the perspective of reference frame A. And what you will find is that in that case, C and B become a product state, and B actually is now in a totally peaked position relative to A, while C becomes ends up in a superposition of states.
So may I, this is the entanglement is perspectival.
Yeah, I mean, so in some sense, yes.
Brilliant. Was it observed before, or is that?
Well, not in the sense, no. So I mean, this here again, this is something that so I was not involved in this here. But now from embedding this in this perspective-neutral framework, it's actually quite easy to see why you get this frame dependence from frame dependence of superpositions and entanglement. It has to do with the fact that when you go back here to this structure, so this physical Hilbert space here, due to the different ways of writing the same, the physical Hilbert space, you write the same physical state or the same physical Hilbert space in different tensor factorizations relative to whatever from the perspective of A, of B, C, C, and so on. And from the perspective of B, so and it's the same, but it's the same states. You write in different factorizations. And of course, different factorizations give you a different notion of entanglement and so on. So using this perspective neutral approach, you get a very natural explication of why that happens. So, okay, so let me now apply this. Oh, actually, there was a question.
Yes. So I've heard of people talk about this work. They say there's something operational about it, but I never got what is operational about it.
About this work from Samini and so on, I guess you should ask one of the. I say it on my slide, operational. Oh, you mean the, sorry, you mean the operational consequences. Oh, that's what you mean. Oh, sorry. Well, I mean, operational in the sense that in principle, one would hope that this is something that one could measure, of course, in the laboratory. How to do that, I cannot tell you. But in practice, but in principle, it should be possible. Oh, I mean, the frame dependence of certain quantum correlations.
The quantum correlations, are they frame dependent or independent?
No, here they are frame dependent. So it depends on what, I mean, it depends, of course, on what kind of correlations you're looking at. But here, for instance, I mean, this is maybe not the very best example here, but I mean, you see here, for instance, A and B, they're correlated, whereas here, so B is correlated with another system from the perspective of C, but from the perspective of A, C and B are not correlated. Of course, we're not talking about the same correlations here, because in the first one here, that's correlation between A and B, and well, now we are in A's perspective, so it's a slightly different notion when we talk about whether C and B are correlated, because they're different systems, that's true. But for instance, what is certainly true here is that you see that B, by being entangled, is in some sense also in a superposition of different locations, whereas here, from the perspective of A, it is completely localized. So that's a,
I guess in the free particle case, as you indicate, you could measure the relative distance from C to A and B, or a relative distance from A to B and C, or even make the full tomography with respect to one of the particles, and then prove that the relation between the states is given there. And the problem of different systems could be solved if you have 4 particles, and you pick up one as a reference frame, and then always talk about entanglement between 2 and 3, either from the point of view of 1 or 4, so that you don't have different systems, you have the same systems, and you can prove that there is a difference.
There is also.
Yeah.
You also have a small comment.
It's obvious after the fact, but it's very fantastic. Sorry.
Yes. So I have a small comment, not much to this, but the question of operational consequences. There is also an important consequence for operational theories. So we know that entanglement is a resource for many tasks in quantum information. Yeah. And here you see that, in many places, you see that entanglement is relative to either some reference frame or some factorization. So I would, my interpretation would be that this brings back the reference frame to become a resource itself. Yeah. So living in a reference frame gives you access to a certain capability, operational capability that you wouldn't have in another one.
Yeah, sure. I mean, this is something that, from a slightly different perspective, has been studied, for instance, by Rob Speckens, Bartlett, and Rudolph, and so on. However, they didn't use this language here, so it's actually quite a different setup without constraints. So it's.
I think it's good to remind that this doesn't make entanglement less of a resource because it disappears in some reference frame. So I mean, it makes the reference frame itself a resource.
No, it's true. So I mean, there you will also find that operationally the access to entanglement is also in fact frame dependent. And so if reference frame A and B don't share a classical reference frame, then what is entangled to A is not necessarily entangled to B because not of having access to full information. But that is actually physically a bit different than what's happening here. But you're right that still one can indeed, that it brings reference frames back to
operational consequence.
Yeah.
Things that you can do depending on the reference frame.
Yes.
Yeah. Why do you call it reference frames but not memories?
Memories?
Right.
Because I'm always describing some part of the physics from the perspective of another physical system, so that's why I would call that reference frame. I mean, it's maybe better to call it a reference system because reference frames we usually associate with whatever a vector frame or something. That's not what's happening here. And also, when you translate this to field theory, then you're working with reference fields rather than vectors and so on. But yeah, maybe I should. Can I go on? Because otherwise I will never finish my talk. So I don't know how much time I have left.
5 minutes normally.
Oh, that's not so good.
5 minutes questions that you can already.
All right. Okay, so it's a bit, I was hoping to be way further. Yeah, so using these tools that we've developed there, you can also apply that now to relational dynamics and quantum clocks. Let me just briefly tell you about the trinity of relational quantum dynamics. So what is that actually? It's using these quantum reduction maps that we've developed. You can actually prove that different approaches to relational dynamics are equivalent. Let me just mention them here for now. There's the so-called relational observables that have been sort of pioneered by Carlo in Dirac quantization. Then there's the so-called Page-Wootters formulation. It's a conditional state formulation. And then there exists also another formulation that is a bit related to deparametrizations, something like reduced phase-space quantizations. And using these quantum reduction maps, we could show that they're actually all equivalent. So that's maybe something surprising from the previous literature, because they were thought to be different approaches. But here what you see is that you can interpret them as, in a way, 3 different phases of the same relational quantum dynamics, which is why we called that the trinity. So the rest of the talk is me preaching to you that you should then believe in this and worship this trinity, and that's the way of doing relational quantum dynamics. So yeah, I should probably say something about why do we actually have relational quantum dynamics? That has a lot to do with the symmetries, for instance, in general relativity, which in toy models amounts to something like a reparametrization invariance. So it's very well known that that leads to so-called Hamiltonian constraints. So it's very similar to what I mentioned before, that rotational and translation symmetry lead to these constraints in the phase-space construction. In GR, it's the same, except that it's actually the Hamiltonian that is constrained to vanish. Just to give you a very brief example, if you take a relativistic particle, special relativistic particle, it has this action. It is actually reparametrization invariant. So if I change that coordinate time t in whatever way, I will leave invariant the action. And if you do a Legendre transformation, then you get that this relation has to vanish. That's, of course, the usual on-shell condition of the momenta for a relativistic particle, but that turns out to be also proportional to the constraint. Okay. It turns out that as a constraint, again, it generates symmetries. So basically, you can think of this as generating active temporal diffeomorphisms. That's what these constraints essentially do. So there's, again, because there's a constraint surface in our phase space with gauge orbits generated by that constraint, the Hamiltonian. And again, we will have a redundancy in the description of our dynamical variables, because of course we have a constraint, there's algebraic relations. And well, similar to before, the idea is now that it's like a perspective neutral, in this sense a clock neutral description of the physics. So it's a description of the physics prior to actually having chosen a temporal reference frame relative to which you describe the dynamics of the remaining degrees of freedom. So what's the idea then? We have to pick some dynamical degree of freedom among our phase space variables that somehow parametrizes the flow of the constraints nicely. This has also been pioneered by Carlo. And then the idea is that we ask for the relations or how other degrees of freedom evolve with respect to that. And let me just say that here for the remainder, I'm going to restrict to Hamiltonian constraints which have a particular form that allow us to split it into a clock part and a system part, and that there's no interaction between the clock and system. The reason we make that assumption is so that it actually allows us to prove various statements rigorously. So now, how do we actually describe a gauge invariant notion of dynamics when the time evolution generated by these constraints is actually also a symmetry? And that is done by doing so-called relational Dirac observables. So this was really advocated by Carlo in the 90s. And then Bianca Dittrich in the mid-2000s developed a full-fledged systematic construction procedure for such observables, even for field theories, any classical system that you want. Here, for our purposes, you can write them in this form. That's just an n-nested Poisson bracket. You don't need to worry about the details of how it's constructed, but more what does it actually stand for. So this is a function on the constraint surface. And this encodes the value of that function f associated to the system of interest that you're interested in when the clock t reads the value tau. Okay, so can be understood as you have a surface, the intersection surface of the constraint surface where t equals tau, and then you ask for what's the value of fs on that surface, and this is a gauge invariant extension of it. Okay, and now it turns out that this construction here that commutes actually with the Hamiltonian constraints. So in a way, it is a constant of motion, but there's a notion of evolution left in it because that parameter tau can run now. Okay, so tau is now just a parameter. It's not a dynamic degree of freedom, and this is why Carlo actually called that evolving constants of motion. And you can think of the gauge invariant dynamics here as being basically you take that t equals tau surface and you scan through your constraint surface, and then you always look at what are the values of the functions of interest on these different hypersurfaces. And now when we go to the quantum theory, well, again, we have to, just like before, we have to impose the constraints. That leads to so-called Wheeler-DeWitt type equation. It's often called the problem of time because now where's the time variable there? The idea is, of course, that what has actually happened here is indeed there's no external time coordinate, because when you think about generativity and you were to do that structure for generativity, then you're not quantizing space-time relative to some other background structure where you have a background time or background causal structure, but you're actually quantizing space-time. So there's, of course, a conceptual difference between quantizing in space-time versus quantization of space-time. Okay? And so the idea is then that we actually have to extract the notion of dynamics from within the quantum degrees of freedom. Okay? And this is often called a timeless state because of what I said before, but actually for the reasons that I was already mentioning, namely this perspective-neutral approach, that we should rather think of this as being a clock-neutral description. So it's like a description of physics prior to having chosen a temporal reference frame relative to which we describe the dynamics of the rest. It's better to actually think of this whole structure as being a clock-neutral state. So now I don't know if I how much time I have. So
we run out of time, but yeah, how much?
I could go on for much longer, but I think that's not what the audience wants. But right. So I mean, I could describe a bit how to translate these objects into the quantum theory, but maybe 5 minutes or something like this. Okay. Then you just stop me. So let me go back. Yeah. So let me describe part of that trinity here. So this is like the clock-neutral picture, this Dirac quantization. So we start again from what I call clock-neutral states, but now, of course, we make a choice of clock in that description. What we want to do is we want to quantize these relational observables here. And what you see from this is we need a quantization of the nth power of the clock. So now here, it turns out that this is best done in terms of so-called covariant clock POVMs. I don't really have much time to talk about this. Should also say that this is an idea of my collaborator Alex Smith to introduce these covariant clock POVMs in relational dynamics. Turns out to be really powerful. Actually, Misha talked very briefly about those. So let me just say very rough ways of how you can construct something like this. So using the energy basis of the clock Hamiltonian, you can actually construct clock states that behave as such. So they evolve in some sense covariantly with respect to the clock. So the clock readings, well, they behave in a particularly nice way. You can generically construct those. I should say that generically these clock states will not be orthogonal. So, and then you can construct, well, POVM elements from this and the moments of the POVM. And what we basically do is the nth power of t of the clock we quantize as the nth moment operator of that POVM. And if you do that, you can write these quantum relational observables in that funny way here. You can simplify that structure. It turns out that it becomes of that form here. This is a so-called G-twirl operation. It appears in slightly different ways in the literature on quantum reference frames, the spatial quantum reference frames, where you have to deal with compact groups. Here, we're generally dealing with non-compact groups. So what do we have here? We have the the observable of the system of interest and then a projector onto the clock reading tau. And then you're kind of averaging over the group generated by the constraints. And it turns out that that also gives you a gauge invariant observable. And then the dynamics, well, you can describe in terms of, for instance, expectation values in the physical Hilbert space. And then you can let that tau run and gives you a notion of dynamics. Okay, let me just maybe briefly say what the Page-Wootters formulation is. So that's getting a little bit of attention in the quantum foundations literature recently. Basically, you again start from that clock neutral description, but now you condition on the state of the system, on the clock reading tau. So again, here we use these covariant clock states. Then you can easily convince yourself that these conditional states satisfy the relational Schrödinger equation. I should say that what I'm giving you here is actually for non-degenerate clock Hamiltonians. If you have degenerate ones, like in relativistic systems, then what I'm saying here holds per degeneracy sector, such as the positive or negative frequency sector. And then, of course, you can say, oh, now we can ask for how system observables evolve relative to, well, in that time, it's just by using the usual Schrödinger picture. So it gives you like a relational Schrödinger picture. Yeah, let me just briefly say that this approach has been criticized by one of the gods on the problem of time, Karel Kukash, in the 90s. I'm not going to summarize this in detail. Main statement is that this approach would violate the constraints, would lead to wrong propagators and wrong probability distributions for the Klein-Gordon systems. Kind of effectively ended research on this approach for about 10 to 15 years. Turns out that here, using our methods of these quantum symmetry reduction maps, we actually show that one can resolve all of these criticisms. Let me just very briefly say what happens here is you can think of this Page-Wootters formulation, this conditional state formulation, as being in some sense a quantum analog of a gauge-fixed version of relational observables in Dirac quantization. So what you find is that you can use that conditioning here to define you a reduction map that takes you from the physical Hilbert space to the physically allowed system Hilbert space, so of the system that we're interested in. It turns out you can invert that map that takes you back from that Hilbert space into the physical Hilbert space. So you can map the conditional Schrödinger states back into the physical Hilbert space. Using these reduction maps in the inverses, it turns out that you can take any observable here and map it back into the physical Hilbert space, and it turns out that it will give you exactly these relational observables, the quantization of the relational observables that I've given you before. This only holds on the physical Hilbert space, I should say. Turns out that the inner products are also preserved, so these maps are actually isometries. And it also turns out that these expectation values that you have here, they're equal to the expectation values that you have up there. Okay, so you have a full equivalence of the quantum theory, or the relational dynamics, in this clock neutral picture, the Dirac quantization, and in the conditional state formulation of Page-Wootters. Yeah, so I guess I have to finish. So this one can thereby resolve all these criticisms. Let me just go very quickly to the end. One can change quantum clocks basically in the by using these ideas that I introduced before, choosing different subsystems. And then, yeah, here's the conclusions. Let me just conclude. Yeah, thanks for your attention.
Because we have to call Vlatko afterwards.
No worries.
But let's take a couple of questions. Maybe.
Okay.
Yeah. Or comments. Anybody?
What's the main question you want to solve? Is it quantum gravity or is it something else?
Well, sure. That's aimed for quantum gravity. I mean, general covariance is, of course, one of the pillars of generativity, but one thing that has not really been studied is what's the quantum analog of this. So, and then, one of the funny things is that when it comes to general covariance, it is mostly in the community of background independent quantum gravity that people actually appreciate that general covariance and diffeomorphism invariance, active diffeomorphism invariance, are not actually exactly the same thing, but that one implies the other. And then in background independent quantum gravity, people worry very much about imposing active diffeomorphism invariance. It's the invariance under constraints or imposing the quantum constraints. But in my opinion, in that community, in particular also the quantum gravity community, they've then forgotten to ask about what actually the more operational meaning of general covariance means. And that's, of course, trying to describe the physics relative to different choices of reference frames. And that's, of course, what I'm trying to address here.
This is a question on, like, what's the operational meaning of going to the reference frame of a particle? I mean, can I do this like, it's a particle in my lab, can I go to the particle as a reference frame? What's the operational meaning?
Yeah, I mean, of course, this n-body, this relation n-body problem is, of course, in some sense a toy model to illustrate how this scheme works. But the idea is, of course, that the general structure of what I'm constructing here, that this will also apply to field theory. So then you will have to deal, of course, with much more complicated reference systems, reference fields. And how you then want to actually construct laboratory situations out of that is a wholly different question. That's very complicated because this will be generically state dependent. So that gives you some effective regimes where some degrees of freedom may behave nicely, that you can model that as a laboratory. But so that will get you into, that may also involve renormalization and so on. So that you will get a whole host of new complications that you have to deal with. But still, the general idea is that using the symmetry principles, even in those situations, that some of the basic ideas will still apply there. Yeah.
If I may add, I think that there can be a simple operational analysis even for the n particle thing. It's just that going to the quantum reference frame of one particle means that now if you look at the positions of the other particles, for example, if I go to the quantum reference frame of A, that just means that when I want to look at the position of other particles, I look at their positions relative to A. And you never look at the position of things in absolute space anyway. Even in a lab, you're looking at the spatial situation of one of your particles, is just looking at its distance from different corners of your table. And your table is a physical system. You usually take it to be extremely massive so that it's not quantum or it's not even moving. But in general, you're always going to reference frame. So here it's just picking this reference frame to be a quantum system itself.
So what's new? Like, we've been doing physics all the time. We refer to particles and their positions. And
I guess now you take the table to be quantum as well.
I mean, these structures are quite new, I would say. So these translations between different quantum reference frame perspectives, that's totally a new structural framework. I mean,
mathematically, maybe.
Yeah, sure.
I don't see the operational side of it.
Well, I mean, so the thing is that it allows you to also describe, quantum reference frames being in superposition relative to one another. And that's not something we have been able to describe before.
And what's the operational meaning of that? You can write your state in a superposition. That's like, you do it on a piece of paper, but it's not clear the operational meaning of, if I can be in a superposition to look at things.
Yeah, so I mean, if you really want to make sense out of the operation, so I mean, okay, there's a good part of that question that probably relates to the measurement problem. So one thing that if you really want to make sense out of this, operationally, of course, then we have to deal with measurement interactions and then also talk about what a measurement relative to one quantum reference frame, how that looks like relative to another one. So that has not been included in here. No, I would say so. Yeah.
You can measure distances. If you measure all the distances with respect to A, and if you measure all the distances with respect to B, you can have two different sets of measurement describing the same situation, which are remarkably interesting relation between the result of this different choice of variables.
I mean, it's a very natural also connection to quantum gravity scenarios, the typical one in which you have a mass in superposition. You would like to know how you would describe this if you are on the mass. We always have this external point of view where mass is in superposition and everything is from distance, but this allows you to jump on the mass and
no, sure, but I think his question is more, what does it really mean operationally? So then I think, but I mean, indeed, so I mean, I think what he wants to know is operationally in the sense of measurement outcomes, I guess. That's what you're referring to? Because I mean, if you, but the thing is, of course, I mean, it's not quite so obvious, I would say, because the thing is, I mean, when we talk about something like, let's say projective measurements, do we want to have that on the perspective neutral level? Maybe not, because it's a global description. And then do we want to have that maybe in the perspectival levels? Yes, that's somehow where we should have them, but then how the different outcomes relate to one another. And I think that's really where the crew is lying to address your question, what that exactly means operationally. That's an open question.
Should we?